My name is Tianyu, and I will present our work today. The title of our paper is Diversity for Transfer in Learning-Based Control of Buildings. The HVAC system is critical in maintaining a healthy and comfortable indoor environment. Meanwhile, it consumes a significant portion of the energy. Currently, most buildings use handmade schedules, meaning that facility managers define control rules based on their experience and preference. However, such schedules are usually energy inefficient. After that, some people propose a model-based model predictive control method. They use models to predict the building dynamics and based on these predictions, run an optimization task and calculate the best control schedule to reduce energy consumption. The issue with this approach is that the model is hard to obtain. Building an accurate model usually requires lots of physics knowledge and data. A better system uses a learning-based controller that can learn the control policy using log data or through interactions with building or the simulator. This approach doesn't need us to build an accurate model for the environment. However, it requires a significant amount of time to train the policy. We noticed that it takes about 300 months of training time to find optimal control for a 5-zone building. In this work, we propose a new method to obtain learning-based controller for the target building. We first generate multiple optimal policies from some known training buildings. Those buildings could be the buildings where we already have enough log data, or some simulated structures where training is cheap. We use policy and environmental diversity to train multiple applicable policies from these buildings and form a policy library. Later on, when we have the target building to use learning-based controllers, we evaluate and find the best policy from our policy library for the target building. Therefore, we don't need to train the procedure from scratch, saving a significant amount of training time in the target building. So that's the big picture of our work. Now, I will break down this presentation into 5 sections. First, I will introduce the problem with some literature review and background information. Then, I will explain our method for generating the policy library. Next, I will explain how we can use reinforcement learning to control buildings, followed by experimental results, and finally, I will conclude the presentation with a few takeaways and future work. Early studies can be categorized into 4 different directions, roughly. The first direction is on the rule-based controller, where Ardakanian noticed that the performance of the rule-based controller is highly related to the quality of the control rules. And the second direction, MPC, is known to be challenging for large buildings. This is because the dynamics in large structures are hard to capture by the neural networks, and physics-based models are hard to build. The last two are both learning-based approaches. Single-agent controller that tries to control the whole building using one agent. That is being said, the agent needs to learn everything about the building and control everything simultaneously. Previous work found that single-agent reinforcement learning cannot perform well in large buildings. Also, the learned policy is not reusable in other facilities because of different building sensor deployment and actuator designs. A more advanced learning-based approach is called multi-agent reinforcement learning, which tries to control the building with multiple agents, where each agent is only responsible for part of the control. This resolves the big building problem. But previous study lacked discussion on transferring knowledge to a different building. Our work uses multi-agent reinforcement learning to control the building, and we train both optimal and near-optimal policies from the training building to benefit transfer learning. Some people might think, so what I mean by near-optimal policies? Near-optimal policies are a policy that is not optimal in terms of maximizing the accumulated reward for the training environment. The conventional reinforcement learning algorithms are trying to maximize the total compensation. They only kept the best policy that yielded the highest reward in the training environment, and all other policies were ignored. This makes the policy we obtained explicitly suitable for the training environment. The performance of the optimal policy is not guaranteed for the environment that is different from the training environment. Here is where the near optimal policy is beneficial. In a different environment, these near optimal policies might perform better in other environments compared to the optimal policies for the training environment. An example would be the maze escape game. A general solution to all maze escape games is called the right-hand rule. If, upon entering a maze, one immediately puts out one's right hand, touches the entryway wall, and then faithfully follows the right wall, the exit will be found without fail. This is obviously not an optimal path to escape, but it is helpful because it can be used in any maze. Whereas if we only remember the optimal route for the given maze, we might not be able to get out when the maze layout changes. So, how can we obtain such near optimal policies? We introduce two ways to find near optimal policies in this paper. First, we can find near optimal policies during the training phase by modifying how we train reinforcement learning agents. We also refer this as policy diversity. We add an extra diversity loss during the training to force the agent to find some policies that are different from the existing policy. After this additional loss in the loss function, we are still making the agent maximize their accumulated reward. In the meantime, they will behave differently from the policies that we have seen before. The second approach is to obtain policies from a similar environment rather than using the training environment directly, or we call this environmental diversity. Using environmental diversity helps us find policies that perform well in various environments to cover more types of environment in the policy library. In this work, we control blinds of the building so that the building can either take the solar gain or remove the solar gain through the window. So how exactly do we define policy diversity? We use PPO as an example here to show how we can include policy diversity during the training phase. After adding policy diversity, we have dual objectives. We have the original PPO loss that is trying to maximize the accumulated reward and the diversity loss weighted by a diversity weight parameter W. This diversity loss term is developed by us and can be described by this equation. The goal of this loss is to encourage the differences between current and existing policies. Here, we will compare the training policy with each existing policy once, and we compare how differently they are based on the trajectories we just collected. We calculate the action probability ratio to estimate the differences. The more significant, the better. Then, we want to make sure the existing policy we are comparing is confident in the current trajectory. Otherwise, if the existing policy has never seen similar states in the current trajectory, we do not need to force the agent to behave differently from them. We calculate the existing policy estimation loss to see how well the existing policy performs on the current trajectory. This figure shows the big picture of our work. We start with a training building, a one-story building. We train using PPO with and without policy diversity. When the diversity weight is equal to 0, we remove the policy diversity and obtain the optimal policy. And when the policy diversity weight is not 0, we have policy diversity included in the training. Then we enlarge the policy library using environmental diversity by adding brands to the training building. We then obtain optimal and near optimal policies from this building. And the optimal policy for this building is called policies trained with environmental diversity. Similarly, policies obtained from this building with policy diversity are referred to as the policy trained with both diversity. After we have the policy library, we choose policies from the policy library for the target building using the policy selection method. Our target building is a 3-story, 15-zone building. In this work, we test all policies from the policy library in each zone of the target building for 1 month, and we take the best performing agent to control the corresponding zone. This slide explains how we form the building control problem as a multi-agent reinforcement learning problem. In this work, each agent tries to control one VAV box in the zone. As we can see in the right-hand side figure, each zone will have one VAV box that is trying to reheat and control the amount of air pumped from the air handling unit to each zone. The state of each agent is the knowledge of the current zone. We assume that we have the information of the zone mean temperature, humidity, occupancy, outdoor temperature, and solar radiation, and hour of the day, which is an integer from 0 to 23. The agent is responsible for controlling the damper's opening percentage to adjust the amount of air entering each zone. The reward agent receives the amount of energy they use for the respective VAV box. To evaluate the performance of our proposed methodology, we designed two different experiments. The first experiment is to see the performance of policies from the policy library in the target building before retraining in the target building. Answering this question can help us understand if those policies we trained from different buildings can be used in target building or not, and if finding a near optimal policy is beneficial. This figure shows the performance of the top 100 policies selected from the whole policy library in each zone of the target building. The total energy consumption for each policy on each zone in the target building is evaluated for 1 month, where all other zones are controlled using a fixed schedule baseline. The red dashed line represents the energy consumption if all zones are controlled using a rule-based schedule, and policies trained with diversity weight of 0, or the optimal policy for the training building, are marked as stars. It is noticeable that all stars are on the right-hand side of the bar. This means that optimal policies we obtained in the training building perform worse than some near-optimal policies in the target building, showing that keeping the near-optimal policy is essential in transfer learning. Secondly, all stars are on the right-hand side of the red dashed line. We cannot obtain a trained policy that performs better than the baseline at the beginning of deployment if we do not incorporate policy diversity. By adding policy diversity and environmental diversity, we can find some policies that serves better than the baseline in nearly all zones. Thirdly, we notice that the trained agent varies greatly for core zones in the top 3 rows. This is because the core zone is adjacent to all other zones, thus it has the most complex thermodynamics. Our second experiment is trying to compare different types of diversity and decide how much improvement we can get by incorporating different kinds of diversity we introduced. This figure shows the performance comparison of 4 initial policy selection methods on the target building. The mean and 95% confidence intervals of the total monthly energy consumption is computed based on 10 independent runs. In this experiment, we use different policies as the initial policy and retrain them in the target building. The x-axis shows the number of months we used for training, and the y-axis shows the amount of energy used for a month. Note that the y-axis is aggregated. The green curve and black dashed line are two baselines we're trying to compare. The green curve shows the performance when we do not have any transfer learning, which means we use PPO from scratch in the target building. The black dashed line is the fixed schedule controller optimized by HVAC engineers. We can conclude that the PPO trained from scratch performs the worst because it takes time for agent to explore different states. The blue curve shows when we only have environmental diversity, meaning that we generate different buildings and optimal train policies from these buildings. Because the training buildings is different from the target building, the performance is not as good as other two approaches, even after we add some modifications to the training building. And we can even notice that blue curve cannot beat the baseline. We can see that blue curve is better than the green curve because we ignore some aimless exploration using the transferred knowledge. The most exciting part is the result of using policy diversity and using environmental and policy diversity together. We can easily conclude that the performance of these two cases is significantly better than all other cases, even the fixed schedule baseline. To better look at the result, we zoom in a little bit and only focus on the case that we have policy diversity and both diversity. The result is shown on the right-hand side, as we can see that the blue curve, or policy diversity case, has a broader confidence interval and slightly larger energy consumption. At the same time, the orange curve represents the case that we have both diversity included in the policy library. Therefore, we can conclude that performance of both policies are very similar, but having both diversity performs slightly better than having only policy diversity. That being said, the policy diversity loss we introduced in this work is extremely useful in knowledge transfer when the target environment and training environment are known to differ. Also, this figure shows that introducing policy diversity can help us find policies that perform near optimal in the target building, even without any retraining. To conclude today's presentation, I summarize four takeaways. First, near optimal policies might be helpful for transfer learning. Second, a multi-agent reinforcement learning framework can be used to obtain a policy for each zone in the building. Then, we introduce environmental and policy diversity and explain how we use them to find near optimal policies and generate a policy library. Finally, we conclude that over 40% of the energy can be saved early on when we use policies from the policy library created using both diversity. Note that savings are obtained at the beginning of deployment without retraining efforts. For future work, we plan to investigate how to choose diverse environments. In this work, we only assume adding or removing blinds from the training building. Then, we would like to study the right size of the policy library and the trade-offs between the size and the cost to evaluate each of them in the target building. Lastly, we would like to learn how to efficiently assess and assign policies from the policy library. Currently, we are doing it high costly by evaluating each policy in each zone of the target building. With that, I conclude my presentation and would like to take questions. Thank you for your listening.